We are live.
Now we're live. Everybody can hear us. Hello. Yeah, I guess so.
Yep.
Okay. Sweet. Brilliant. So it's Monday because tomorrow Sophia graduates.
Very cool.
She got that ceremony shit, which I
Yep.
hate going to.
Really?
I know, but she only has like 40 kids in her class, so it's not a big deal.
Oh, okay. So it'll be quick.
Yeah, no. All my kids went to a school where there was like, I don't know, 500 plus kids. I just want to shoot myself. You know? I'm sorry, I don't care about your kid.
that was like for me in high school. I had like I think it was like 300 or 400.
No, it's all day, dude, and they go
Yeah.
up and her well, I'm not gonna tell you her last name online, but it starts with the letter A. So
first.
So
and
she's
then,
gonna go like almost. I don't know if she's first, but she's in the top like 4 or 5, right?
Yep.
And then the rest of that time, you're just like,
you're just waiting.
I'm looking at the door. I just want to get out of here, man. I know. I mean, it's not fair when your last name ends in Z and like everybody's just leaving after the kid gets off stage. That's not cool.
Yeah, exactly.
You know? And then they tell you you're not supposed to clap, but you know, this is
everybody.
Miami,
Everybody claps. Everybody screams.
Tell some Latin person they're not allowed to scream for their kid. Like, let's see how far that goes.
I remember that. Yep.
Anyway, that's my day tomorrow. Plus, we're doing corporate training from 4 p.m. to 8 p.m.
Yep.
All week after all this stuff. So I just can't wait till Friday at 8 o'clock when I'm done.
Friday's going to be a good day.
No, I know. But then next week we have the training from... When is the training next week, dude? That's the other problem.
I think that's 8 a.m. to noon.
That might even be worse, 8 a.m. to noon. But the worst one's going to be 8 p.m. to midnight in like 3 weeks.
Yeah.
Yeah, not looking forward to that at any level. Okay. Anyway, enough jibber jabbering. Let me switch to this. I got to see where we're at.
Yeah.
I think we finished. When did we meet on Thursday?
Friday.
It was Friday. Okay. We finished the foundation package here.
Yes.
The TCP package. I mean, we got it a little bit more, I think, better organized still in one package. And this is something you would never want to split into separate packages anyway, because you want to deliver this API under a single version, right?
Got it.
And so this is how we would sort of do it with these little struct-based APIs, the way we did it, the way we isolated the map handling here, right?
Yep.
Between an API. So at the end of the day, we have and we used an atomic variable here, which I've never done before. And you do have the wait group for the one thing. You know, I was thinking this morning about the API design in one aspect. Where's our hack here for a second? So I was thinking, here's main, right? So we have a function here called start.
Yep. And
start returns, assuming now that you're going to manage the concurrency of your app not sort of shutting down, right? Now, we could have implemented start where it blocks, similar to the way the start listener function works in HTTP.
Okay.
Where it blocks, right? Where now we would have to manage the shutting down of this app in a separate Go routine. Or this would have to be wrapped in a Go routine so main can keep going.
Got it.
But then I realized that the HTTP package for the load shedding actually does the same thing, right? So look, I was just wondering, oops, I always forget. Sometimes I'm moving so fast, I don't sort of see that. Let's just do it. I know it's going to be fast, like updating my show. So I was thinking, I'm going to bring up the service project for a second. Oh, brought it up on my other screen. Hold on. Let me bring it here. So the HTTP package has something similar, right? It's called listen and serve. Okay. which is essentially what we're doing with start. We're listening for socket connections. We're not necessarily serving anything up, but we're at least sort of listening.
Okay.
And it's a blocking call that you're responsible for sort of wrapping around in a Go routine. So you can manage it, and then you can basically on shutdown, sort of shut things down. I was thinking about this API because I feel like maybe start should be similar in nature.
What's the advantage to doing it that way?
I think the advantage is that we're going to. I think it gives the caller a little bit more control over the start and shutdown of their particular app. Knowing that this sort of blocks, you can then sort of write code like this.
Okay.
So look, let's play this out for a second, right? So instead of this being called start, what if we rename this to listen? Okay, because that's essentially really what it's doing, right? The idea is that it listens. Now on the HTTP side, they called it listen and serve. This is more listening and then handling stuff. But what would be interesting here then is this API has the shutdown to sort of bring that down, right? We also have a stop. I'm going to move the stop for a second above it because it will be easier for us to read this code. So what if I call this shutdown? Let's say we model this after the same API. Okay. So what would that mean then? It would mean this, right? We're going to do listen. We still have the wait group add. We still have our done. But what we would do then is after this Go routine got created, let's just say that we did I'm playing this out right now in a hack. Let's just say we did the wait. So that means this wouldn't return at all.
Okay.
Until the Go routine sort of terminated.
Got it.
And the Go routine would say terminate on shutdown. And so the idea here is when they call shutdown, we would set the shutdown flag. We'd reset the listener. We'd close. We know that on the resetting of the listener, it would call the done here. And it would sort of shut that down that way. But it would close all these connections before. So it's always better, honestly, to keep the add, done, and the wait in the same place when you can. And this is kind of doing that, right? It's keeping the add, the done, and the wait sort of together.
Got it. Okay.
Okay. Now, what gets interesting here is if I do that, we'll deal with the test in a second.
Yeah.
Now, what that means is that this listen now is going to block, right? So what if we did the same sort of thing that we do here? All right, we call sort of listen here. And if I looked at this, right, we just have a log that says sort of started. And then if it errors out, we have an error channel here, right? So what if we did the same thing? All right. And then here we just say start listening, right? Okay. So we've got the same sort of mechanic here. And then the idea is that we have to hold the server sort of down. So what we can do is sort of take this, all right? And this will allow us to do in our case, we just care about SIGINT for our purposes, but that's fine there. And then we could do really a proper sort of shutdown mechanic where if we get an error, okay, we'll return the error, that's fine. But this obviously will now have to be a funct because we don't really have a logger in our tiny program here.
Got it.
Print line. We got that and bumped up print line. Let's put this here. So was that in a defer? It had to be in a defer. Okay. Yeah. So now we don't have a context here where we're going to wait for a certain amount of time because though I know I had a to-do about
To add
the
that,
context,
yeah.
right? So this gets interesting because if I put a context here, I can't really, well, we could solve this problem. So let's just do this for now with the idea that there could be a context that says how long you're willing to wait for the shutdown to actually happen. I don't know what mechanic I would necessarily put just yet, but let's just say that we had that where this would be you sort of shut down. The idea of close in this case is you timed out, so we got to just shut everything down sort of hard here. This would be context.background just to start with a new one. And right now we don't really have anything here to deal with, but whatever, not Saturday, but like second. So we'll deal with that in a second, all right? But the idea here is once we hit Control C, then we'll call shutdown, all right? And shutdown also doesn't really return an error. We'll fix some about that. But now this sort of goes away. Now, the problem here is this code was testing stuff, okay? So this code now would never run technically sort of where it is. I'd have to put this now in a separate sort of Go routine.
Got it. Okay.
So what we could do, just to sort of play this out, I don't even think I need this at all, but I had a function called TCP client, which literally did all this. This was just testing that we could connect and send and all of that, right?
Yeah.
Okay. And so what I would say to you is that in our little test program, right, we called new. Now in this Go routine, we called sort of start listening. And then we had this whole sort of shutdown mechanic, right?
Yeah.
What we could do is put this in a Go routine here. All right.
So now it's two Go routines.
Technically, yeah. So there's three really. It's the main Go routine, which we're managing a more server-centric sort of shutdown.
Yep.
Here, we're starting the server, right?
Uh-huh.
And then here, we're running our test, right? This is our client test.
Got it. Okay.
Right? That's our client test, which will now sort of run this code here, trying to connect to that server and do certain things. Now, it looks like we did need our TCP config, didn't we? So
For those.
that was kind of, it knew that already. So we could put our CFG here. All right, because we just needed these two things and I just sort of passed that in. But this is more server-centric now because the idea is that we start this in a Go routine. If it errors out, we can manage it this way. Also, we'll be able to do more shutdown stuff, which we're going to do next. But ideally, if I run this code, now our test is not happy because our test now gets much more sort of complicated to write, right? Because this now essentially blocks. We'd have some of the same problems here, right? I wouldn't even know where to sort of begin with the test now because that has to run sort of in its own Go routine. Now that would be fine almost. And then everything could run. And then once everything runs, yeah. All right, then I could do a u dot shutdown. And I wouldn't particularly care. And I just want this to sort of go green. So same sort of thing here, right? At some point, we're going to need to run these tests to make sure this
Yeah,
thing works.
to make sure.
But the general idea would be, what did I do wrong here? Oh, go routine calls t dot fatal. What did I do here? Yeah, it can't call t dot fatal. It can call t dot error though. All right, t dot error, and then we'll just do the shutdown here. Okay, so just to make that go yellow for now. Now there is more yellow here, so we're not doing something right on the linter side. Condition is a nil equals nil. Yeah, so, oh, this is on the connectivity side. So let's play this out. Oh, once I did, see, I love linters, right? Yay for linters. That would have been a nasty bug back in the day without the linter, because suddenly this was its own local variable.
Oh, okay.
Right?
Yeah.
And it wasn't that. So the linter sort of saw that. Yay for the linter. We would have been scratching our head for an hour.
A colon. Yeah.
Yeah. Okay, let's just see if this code runs. I'd be happy if it did. Oh, wrong window here. So that's good, right? Start listening. It did this. It did this. Now I saw client G stopped, but the program didn't die. And that's because it's in server mode. So when I hit Control C, then it says, okay, shut it down. So this is what we wanted. Okay. We want to be able to trigger sort of the shutdown, right?
So that's the advantage, is that you have control over. Okay,
yeah, but we're going to have that because we're building this into a service. So we've got to be able to control shutting this down on that sort of event, right?
Got it.
And we saw that the client G stopped essentially on the drop because we must have, I don't know if this code drops the connection or not. So that's weird to me.
But it was too, oh no,
oh yeah, defer the close. So once this function returned, it dropped the connection.
Okay.
So like everything we're seeing here is, and this really here shouldn't be stopped. It should be disconnected. I mean, it's much more sort of accurate. So you see now how we've got this running in a much more sort of server-centric way. All right. Now, again, ideally, we want to shut this thing down within a certain amount of time.
Yeah.
Okay. What's holding us back from shutting down is sort of this loop, this closed loop. Because what if there's 100,000 connections and we're supposed to shut down? And now, I don't think this loop would ever really cause sort of that pain.
Mm-hmm.
We know that this listener is immediately shutting down once we sort of drop it.
Yeah.
And we sort of see that because we saw event stop info. So started shutdown, completed shutdown, right? So we see this here, started, completed. And then we see this is the shutdown listener, right? Or completed. I always like the idea of completed, right? Maybe this is completed listener shutdown. And then there's a sort of start to this, which is potentially here, right? Shutting down here. So So you see what I'm saying? Like once we know that we're shutting down, this listen reset is going to cause that sort of
Got it.
situation because this will error. We'll come back to the top. Then we'll see that we're shutting down. So now if we look at the logs, so the two clients went and disconnected.
Yep.
I hit Control C. Now we saw this already. We see the Control C and we see shutdown started, completed. Now what I didn't see, I saw this, right?
Yeah, but we didn't see the other.
I didn't see
No.
this happen. And again, it's a timing issue around because we didn't really wait for that log to happen. Though I would have assumed that we would have saw this. I would assume we had saw this started. That's interesting to me. But again, it's a timing issue.
Okay.
We know that this is a synchronous call. We know this happens within the scope of this synchronous call because there must not have been necessarily a context switch that sort of occurred.
Got it.
Now, if this would wait for this, right, to happen, which it could potentially, I've never like done anything like this before. Can this sort of wait for that to sort of shut down? Like we've got two areas of the code that are sort of waiting. Now because they're both waiting for that event, you have completed listener shutdown. Now, what I don't still see, so let's talk about this because I feel like we saw this.
But we didn't see that one, the started listener shutdown.
No, we didn't see this. I also, interesting. Because the moment we shut down the listener, we should have seen stop info started, completed. I like this. Like, I love everything that's happening here. What I find interesting, we didn't fail here. That's why. We're failing here. Okay, this is what's happening here. Oh, we're in this right here. It wouldn't have been here. I know what's happening. Here's, are we shutting down? We've got it in two places.
Okay.
Remember, this is the error, right? Because we dropped it. Then we asked, are we shutting down? So here we're starting listener shutdown. And then we broke out of here. So we never got in here. We would only be in here if we're unable to start the listener. We don't have a network.
Got it.
So I missed the logging sort of in this inner loop. So now if we run it again, now we see started,
completed,
we see shutdown. And we have this waiting as much as this is now waiting for the G, and that's giving us enough of the managing of the concurrency to see what we need to see sort of in the logs.
Got it. Okay.
All right. Where before, that's almost being terminated before, right? Because main is terminating first. So we don't see that. This is the concurrency.
Yeah, so it was, okay.
Right? Now, the problem here with using the wait group is that we're not able to shut down earlier if there's an actual timeout. So we're going to have to wait for all of this to happen, right? In this particular case, there's no way to just say, hey, this all has to go down and that's it. Imagine a scenario where we have a go routine. Well, this is just accepting, right? Starting a new client. But it's this close. I bet you the close waits.
Yeah. Wait.
Yeah, but that's just another wait group, and that's dropping the connection. So, but it's a wait on that connection, and it only gets called done here. So you see, you have a second level problem. Let's say that we're let's say for some dumb reason, and we can simulate this, that somebody is blocking on this right here.
Okay.
The server will never shut down. It will never shut down.
Oh, how come?
Because this wait will never fire. Because we're not getting out of this loop.
Oh.
Right? We're in a read call. That read calls that read function.
Mm-hmm.
Well, it doesn't return. If it doesn't return, we can't get to doing any of this other sort of logic.
Got it.
Okay. And I could easily simulate that by like putting a time dot sleep here worth, 100 seconds. Okay. Now, our client code won't work really well because we'll never get the read back, but the server won't shut down either. So that's blocked because we're not listening on the read. Now I hit Control C, we can't shut down.
Oh.
This is bad, right? Now we've got a zombie sort of process.
Yeah.
So you got to deal with that situation, all right? Now the only way to deal with this at this point is to go hard here. Okay. And probably even have to kill this. But, okay. So you see what happened there? Yeah. This misbehaved. And so when that misbehaved, this really couldn't sort of shut down because this wouldn't time out. So you either have to tell somebody that read can't block for a long amount of time, or we've got to handle the concurrency sort of around that. All right. Because regardless of this returns, so this would then have to be in its own sort of go routine, and we'd have to use our own mechanics to wait a channel that gets it back to wait on it to, but let's just look at this for a second, okay? Because assuming that I could solve the same problem right here too by not wanting, like by letting that happen and wait for it to finish, but if it doesn't finish, then we're good. So look, so watch. So I could do the following in here. I could say that this call potentially can block because close can block.
Okay.
All right. So given a context, what can we do here? I could put this in a go routine. So let's start with that. All right. I want to wait for that to finish, all right, before we do anything else. But how long do you want to wait for that? The question will be on this particular context.
Okay.
Okay. So what we could do maybe is context has a done channel. So let's say I said this. We're going to wait for context to be done. Now, the problem here is I can't call cancel on this context, which is what I would want to do to make this all work.
Okay.
So I can do the following. All right. I can say context cancel. I can do it this way because that's a new variable. Context with timeout. But instead of using with timeout, I'm going to say with cancel.
With cancel. Okay.
Okay. So given the context that's passed in, I'm going to say with cancel. And then what I'm going to say here is defer cancel.
In the go routine.
In the go routine.
Okay.
And then I'm going to wait. So two things can happen now. It could be canceled because of the timeout that we inherit, or I call cancel on this and because this operation is finished.
Got it. Okay.
And now we're sort of getting out of there, and then I'm still waiting for this to happen But remember, this is just so we can sort of get some logging.
Yeah.
This is an independent situation. What was blocking here is on the close. So if I do this and just run our, just keep this in case I need it. If I do this now and run the make hack, everything should just work the way it did. It did. We've got the two things. I hit Control C, it all sort of shut down.
Got it.
Okay. Now I could come back here and again cause the deadlock to happen, right? Sleep for let's just do 100 seconds again. Okay, so this is gonna deadlock. All right, but we're still wanting to shut down here. This is the shutdown here. So what if I said you have a second to shut down?
Okay.
Right? That means we should be waiting a full second, and then our shutdown code now should do the cancel here when that's done. We won't know necessarily if we can test it. We can say if context error doesn't equal nil or context canceled, right? Then we could log canceled shutdown.
Okay.
Right? In this case, we should see if it's not nil and it equals
Context.
canceled.
Oh, okay.
Because there's two of them. I don't know why. There's canceled and I don't remember what the other one is. Canceled.
I saw
deadline exceeded.
Oh, okay. That's
But we're not using deadlines. So I think we should see canceled shutdown on this one. If that's the that's the reason why we get through it. So let's see what happens now. So I'm gonna now hit Control C.
And it shut down.
It did shut down. I didn't see, however, what I wanted to see.
Yeah, like cancel.
So let's do this instead. It's not nil, right? All right. Canceled shutdown. There it is. So it must have been the other one. But you see what happened now is that we take the existing content, create another one with a cancel. So when it's done, we can cancel our local, or we're still going to be bound to the timeout on the parent context that's being come in. And this is a situation where we're like, we can't shut down sort of cleanly anymore. It sucks, right?
Got it.
Now, the HTTP package, what they did is the shutdown, if it waited, it would return, but it wouldn't be sort of self-destructive. This would be, I don't care what's going on. We're done, right?
Got it. And
we could implement the same thing technically. You see how the context is here, and this is just a complete code. I wouldn't do that. I think having the context here is fine. They may have had other reasons. But this now bypasses a situation where that one go routine is sort of blocking. Now, what stinks here is the other go routines might very well be able to shut down. Okay. They might be able to shut down. Okay. So ideally, maybe what we need this in the go routine in order to go down. But it would be nice if these sort of ran asynchronously, because if we look at our output, if we looked at your output before, you don't see any of the connections sort of dropping, and there should have been two.
Yeah.
Right? So we've got the client G. Oh, but the next one doesn't connect until, well, let's take a look at our hack program for a second. Oh yeah, we didn't start both of them. We did one after the other, right?
Okay.
So if we want to make this a little bit more sort of fun, I'm having fun with concurrency today.
Yeah.
Right. Oops. I think it has to be here. Okay, I know you can't do that anymore, and this wouldn't make any sense. And now we're just going to launch 2 Go routines to do their own sort of thing here. So
now they're both going at the same time?
yeah.
Okay.
But that's the only way to show what I want to show, right?
Yeah.
So you'll be a print line here, and now you'll be a return. And if that, you'll be a print line again. You'll be a return. It's fine. And then you'll be a print line again. Now we're going to have to put the number on here for the connection because this is concurrent now. We don't know which one is which.
Oh, okay. It'll just, yeah, there'll be, the logs will be.
So maybe something like this, right?
Yeah, just put the number in front.
Now it's going to be crazy because now they're both sort of running concurrently. Neither will be able to complete because we're blocking both of them.
Okay.
But let's see what happens. It would be nice for my little test that one sort of works and one doesn't. But now, oh shoot, we're gonna shut it down probably. So now it gets interesting, right?
That 100-second sleep is still there?
Yeah, we have the 2 connections, right? This loop I put in there because we weren't sure if we were ready to connect, right?
Okay.
So I kind of put this loop in there. But let's say that I just got rid of the loop altogether for our purposes here. Just got rid of the loop here for a second. And we're just waiting 300 milliseconds. All right, let's do it again. So trying connection 2, trying connection 1. You see concurrently they're out of order. The connection must have happened. They both send hello, but we're blocking on the read because of the bad code. So I've got 2 Gs now that are started. Now, when I hit Control C, they're blocked. We couldn't get them back. What I wanted to test was the case where we only blocked on one of them.
Oh,
right?
Okay.
So I'm going to do something really, really bad here, okay? Like really bad, data race bad, but it's just super fast way for me to do it. And even this may not work because none of this is synchronous. Let's do it this way. The only way to make it synchronous. Atomic dot, say N64 bill. Bill dot, remember the load command. If it equals 0, then bill dot add 1 sleep. Even that, they might both run load at the same time. So even that doesn't necessarily help us. This is where you need the compare and swap. So we want to compare 0. And if it's 0, make it 1. All right. And then that returns bool. So this is the only way to do it because the whole thing has to be in an atomic instruction. I could do load, set, but the Go routine could context switch after the load and they both see 0. But with compare and swap, what it's going to say is if the value is 0, set it to 1 within the scope of the same lock.
Got it. Okay.
Okay. And then just do the sleep. So one will block now and the other one won't. So you see one of them went all the way through.
Yeah.
The other one is blocking. Now when I hit Control C, the one that we could disconnect now can disconnect. We did that off of another Go routine.
Got it.
The one Go routine that's blocked, well, that one we have to sort of cut out its legs. it's not perfect, but it's working better, right?
Yeah.
Because now we're able to shut down.
And for the ones who are connected and went through the right
The ones
flow,
that are
they
sort
get
of,
shut off
yeah, I mean, it's
gracefully.
blocked here. So now that's a bummer. Maybe it's actually doing something sort of nice, and it would be nice to tell it that you need to cancel what you're doing. Okay, so how can we do that? Because we've solved it at the high level here. Okay, but ideally what we want to do is pass the context into close. So if close took a context, okay, now this is a connection, this is a wait, and this is our problem here, right? It's the wait that's not returning. And so we're here, we need to pass a context into this read. We don't have a context right now in the read. And essentially, we only want to wait. We have the same situation, right? We only want to wait on the context related to that client connection. So what we could do, normally it's a smell when you do what I'm about to do here. But I think we're going to have to get rid of the wait group here. Let's play it out.
Okay.
Let's say I put a context into this TCP, right? And what we're going to do on the creation of this TCP, I'm just looking at the order of things, reader, writer, time, here. I do a background, okay? So it's got a general background sort of context. Now, on close, what do I want to do? The problem is that the context that this read can leverage is this one. Okay? It's not this one. And I just want to look at something here. The problem is I can't take this context and change it. I can look at its deadline. I can look to see if it's done. I can get to the value bag. See, this isn't going to work because I can't change the deadline of this context. And I can't, this is complicated.
Yeah.
It's complicated in the sense that this context is related to this wait. But I can't, and this is what's triggering this to shut down. And actually, that's not triggering it. This is triggering the shutdown event. Because if we're blocked in a read on the connection, that would automatically close it anyway. What I did is I created a bad situation where we're not in the read. If we were in here, it all shuts down. I'm like here. So the problem is that the problem is that that read needs a context that it would respect. But at that point, it doesn't really make any sense for us to have the context. It would be up to the person that's implementing this. So what I would say to you is, I don't think this is anything we can do here. All right. There is a shutdown that we can do, but we can't necessarily do it here. This would have to be our responsibility in here to handle what's happening here. See what I'm saying?
Yeah.
There's just no way to tell it because we're in a read, we're not in a shutdown situation.
Yeah.
The shutdown situation is happening here where we're going to close the connection and then wait for that to happen, but it may not happen. So I like this here because this isn't serial anymore. We're just going to throw a bunch of go-routines at closing these socket connections.
Okay.
This may or may not happen, right? We may or may not get past this.
Okay.
because the calls that we're making, say to the user level, may or may not return.
Oh, okay. I see what's
But I
happening.
want to shut down as many of the connections as I can within the
Yeah,
scope of this amount of time,
got it.
right?
So by doing this go routine for the close, it's just gonna close
As many as they
as
can.
it can. Yeah.
Because if one of them is blocking, then we don't close any of them,
Yeah.
which you just saw in the output here. Right now we're seeing client G disconnected because that one was shut downable,
Yeah.
but we don't have a zombie process,
Yeah.
right, on the ones
Exactly.
that we can, which we were going to have.
And that was because we were going serial, like in
That
order, one
there
after
was
the other.
serial, but the bigger thing is this whole function doesn't return until either this is done or the context times out, which we have here. And this is just a synchronization mechanic for ourselves to help with the logging.
Got it.
Right?
Okay.
They're both sort of waiting. Listen isn't going to return until this done gets called. So it's a very much controlled sort of shutdown. We have logging for it. Now, this means essentially that when we write this, we have to get in and out of these functions as quickly as possible because they can prevent us from being able to shut down in that reasonable amount of time. Because we're not gonna wait for as long as this, and then we're just gonna knock the legs out from under it.
Yeah, and everybody's
Right.
going down.
There's no way to really tell it it's in a shutdown mode here. So that's gonna be that. We can just keep this little hack in there so we know it's working. So I think we've got that problem sort of solved now, right? We went into more of a server mode where we listen and then we hold for any errors coming out of that, or a shutdown where we just call shutdown.
Got it.
Okay. And if it times out, we know what happens there. You get this. Now, we didn't actually do that right. We should return an error from this.
Oh, so that call can, or
Yeah.
that can error out.
Yeah, should do that. Now, why does it not does this not return an error? Oh, that returned an empty struct. Oh, this is what we want to return anyway. That. So I don't need this. So that's what we want. This should return the error, right? And we just have an event for that as well. But most likely we'd be logging it. Couldn't stop the server gracefully. So now we've got something that's highly sort of concurrent, right?
Yeah.
All right, let's we're fixing the concurrency. To try to do any more at the client connection, I think is overkill at this point. Because we're going to wait anyway for a certain amount of time for all that to happen.
Yeah.
And if it doesn't, it's like we wouldn't be able to do more anyway. So just by waiting here, it's giving these go routines enough time to shut everything sort of down.
Got it.
Now, if there were 10,000 connections, there'd be 10,000 new go routines that we launched. So we would want to make sure that we had, and it's not the number of go routines, no big deal. We just want to make sure that we're giving this enough time.
Got it.
Like 1 second is maybe not enough time, right? You'd want to give it maybe 5 seconds or 10 seconds, whatever the shutdown is. But
and creating all those go routines, is it still like pretty fast,
yeah,
or is
it's
it?
no big deal. It's no big deal. So pretty cool though, right? Now, modeling after things that the standard library does, sometimes it's sort of nice. But now we can incorporate this into our sort of server much better. Like if we go back to the cap for a second, cap already has this.
Yeah.
Right? There's a shutdown sequence. We're going to add to the shutdown sequence now, where it says API shutdown. We're going to now add, in this case, use shutdown, right?
Got it.
We'll call it TCP, but now we can right? We'll shut down our TCP connections, and then we'll shut down the API first, and then we'll shut down our whatever order you do construction, you do in a reverse
Got it.
on the
Okay.
destruction. Is normally like it's a smell if that doesn't make sense. So if you brought the API up last, you should bring the API down first.
Got it.
Because you're bringing up the API last because it needed all these other resources. Well, you can't shut down the resources first.
Oh, okay. Yeah,
right?
yeah,
Because
yeah.
now you might have things in flight that we're using.
Yeah, you're going down this way, then you gotta
if you go
go
right,
the other
if
way.
you construct this way, you got to go.
Exactly.
Yeah. All right. So we have this now. We're able to fit it into this sort of. You see the paradigm here.
Yeah.
So we'll have the same sort of thing going on there. Now, I've been thinking about this pretty seriously. I'm going to bring back this right here for a second. Man, everybody's been quiet today, but okay. Let's just come in here for a second. So I've been thinking about this. Right now, what we have, we just talk about you and me for a second. We each run a cap, okay? And that cap currently connects to NATs up here, right? The free sort of NATs. And the NATs gives us that communication back and forth. And then we run a UI here. We have the terminal UI, we have the data star UI, though that might be broken. And it establishes, in our case, at least with the TUI, that sort of socket connection, right? And this is how we do it. Now, we've been talking, everything that we've done so far is essentially for this. That cap can connect to this and this. Oops. Okay, I don't know why you're behaving this way. So, whoa.
I didn't even know it could curve like that. There.
Yeah, I don't know why it's doing it at all. And I didn't know it could do that either. I don't know what mode I was in. Dude, I didn't even know what mode I was in. That's insane. Now I'm going to have to,
That's pretty cool though.
Okay, so this is what we're trying to do. And right now we're on the same network. So
which is peer-to-peer.
This is peer-to-peer.
That's peer-to-peer. And this one is when you say like spoken wheel?
That's client server.
Okay, client server.
So you can consider this spoken wheel client server where this is centralized, right? The whole thing about here is that we still have a centralized sort of system because everybody's got to connect to this centralized system in order to communicate. Now, luckily, there was no authentication to connect to this centralized system. And we did do decentralized ID identification through our ECDSA work.
Yeah. That.
Now, ideally, this is what we would call decentralized in this case. Because ideally, if another cap came into play, right, then these two caps could peer-to-peer, and these two caps could peer-to-peer.
Yeah, they're not having to go through that central NATs first.
And so this is when you you might start hearing words like mesh networks and things where everything's sort of connected together where it needs to be connected. The blockchain works very much like this, except, when you have 5,000 nodes, like Ethereum today might have, there may be 5,000. Let's see how many Ethereum nodes are like in production or something, right? So, all right, so Ethereum nodes online. I don't know if this will tell me how many Ethereum nodes are communicating online right now.
Might have to put count. Nodes count.
Yeah, okay. That's a good idea. Number of. Okay, so there's 8,600 nodes right now running. If you just look at Ethereum, all right. If we look at Bitcoin, there are 22,000. Okay. So what was the other number again? 8 and 22,000. That's a big number. So in a decentralized system like a blockchain that gets to those numbers, you can't have every Ethereum node connecting to every other Ethereum node. Okay. It would be too much.
Yeah.
Way too much. There's a couple of nodes out there that everybody knows about. And you may start there and ask, hey, let me see your table of things, right? But ideally, in a system that's going to be that decentralized, what you're trying to do is create like regions of nodes. So imagine you have a region of, I don't know. I don't know what the average number of nodes on Ethereum is that really sort of talk to each other. Maybe a given node might talk to or connect to 10 other nodes, let's say. I don't know what the number is. But let's just say there were 5 in some sense, right? So you can argue that like these 5 nodes are talking to each other. They're in a mesh.
Yeah. But
then at some point, these nodes are also talking to each other. And so this is how a transaction would cross sort of boundaries, let's say.
Got it. Okay.
You see what I'm saying?
Yeah.
Because you can't have everybody connecting to everybody. You've got to be somewhat smart about that. There's network latencies, there's connectivity. You're trying to get your thing out. And so I'm sure somebody's done some math to determine what's the optimal number of
connections across.
So if we go back here, maybe number of Ethereum nodes online, it was 8,000. So number of Ethereum nodes, maybe that connect to other Ethereum nodes. Like, I don't know what these numbers are, but now this is saying there's 300,000. I don't know.
Yeah, like here, this one says the node. That's a node tracker.
Oh, let's just read this real quick.
300,000.
Yeah, I don't know if that's. So I don't know if I'll get this answer here, but
10,000 nodes found. That's what it says.
Yeah, but I want to know if I brought up an Ethereum service, right, which I could do right now. I'm going to go look at the core 2 of them. I might even connect to those 2, let's say. But right, every node isn't directly connected to each other, right? This was, all right, let's just look at this real quick. I'm just trying to get you a general sort of understanding here, right? Each node is connected to a few other nodes. I was looking to see if we knew what that sort of number was.
Got it.
I don't know what the number is. Let's say it's somewhere between 5 and 10. I don't think you would need sort of more. And maybe there isn't necessarily an average. I don't remember some of this. But it looks to me like there's really just 8,600. And they've changed some things now with the way, like when we did proof of work, it was much different. Actually, I shouldn't even be using Ethereum anymore because they're not doing proof of work anymore. They've got another strategy. Bitcoin is probably better because they still do proof of work. And so all the nodes eventually have to know what the network is like. Ethereum sort of changed everything.
Got it. Okay.
So it's not really telling me anymore here, right? Yeah. So at the end of the day, I'm going to move on. So at the end of the day, and Bitcoin is a better thing to talk about because they're still doing proof of work. Not every node's connected to every node. There'll be a region of nodes that are sort of connected to each other, and then nodes that are sort of connecting that region. This is still highly decentralized.
Yeah.
Right? And in the case of a proof of work, decentralized proof of work system, say like Bitcoin, you need to make sure that 51% of these agree with the same blockchain that you think you have on your local disk.
Oh, okay. And that's part of that algorithm that we had talked about?
Yes, it's the proof of work. So if this machine found a solution, which is essentially given the data that you want to add to the blockchain,
Yep.
hashing it with this nonce,
Yep.
we get, let's say, so many zeros in the beginning of the hash.
Mm-hmm.
You found a solution. Now you're racing to send the solution out with the data to every one of these nodes. This guy may have found the solution right before you or right after you. He's pushing out the solution too. The first solution that comes into this node and checks okay, he's going to accept. So this network would probably accept his solution. This network's going to probably accept his solution just because they're closer.
Yeah,
You could get it to them faster. The question is, how fast does this set of nodes get it? And at some point, when the next solution is solved, they've added it. Now we know, right? So this guy accepted this solution plus the next one.
Yep.
Let's say he accepted this solution plus the next one. These might be his, and then the next one. Eventually, somebody has to say, "Oh shit, I got the wrong one," and I only have the wrong one because 51% of the other nodes. Because every time I get a new solution, it's based on his, not his. So over time, it's like, oh shit, it's still hit. Oh shit, it's still. Oh, you know what? He won. Now I got to roll all that back and come back in. See what I'm saying?
Yeah.
Keeps it, but it's decentralized because it's the majority of the nodes who are agreeing who won that.
Yeah,
that
it's
round.
not like one central.
No, but Ethereum sort of moved in that direction now, where they pick the person who's going to solve the problem and provide the solution and at a high level. And
Got it.
what they do, which is super cool, is you've got to know who's going to be next. So given a set of nodes whose job it is to solve the solution, how do you randomly choose which node is next? But they all know that's the next node.
Yeah, that's
right.
Yeah.
And that's done by basically running an algorithm on the data that randomly picks one of these nodes that they all would, the algorithm runs the same if you run it against the same data. So given the same data, this random algorithm will pick the same number. So it's
random, but not completely random.
It's not completely random because it's based on the data.
Yeah.
But it's random because until you run the algorithm, you have no idea what number it's going to pick.
Yeah.
But they all end up getting the same answer. So given that the blockchain is the same on each of these nodes, when running the algorithm, they all know that person's next to do the job.
Yeah.
Right?
Yeah.
But it's really efficient because we're not wasting CPU cycles on everybody trying to solve the zero problem.
Exactly.
It's right.
You know it's going to be that one.
That's it. Yep. Okay. All decentralized. So in our case, since we're going to be small, right, we could do a full mesh. We could do that. But I don't want to do that. What I'm thinking is that we keep NATs because NATs is pretty cool, right? It gives everybody the ability to sort of come in. And for basic messaging, I would keep that. What I'm thinking is the following. If two people not only share their ID, but share their, say, IP address.
Okay.
Okay. And that's in our system. So let's go back to this for a second. Client, database, data JSON. Okay.
Yep.
We'll add another field here called
IP
host or something, right? Okay. IP, say we call it host. Now, if it's there and we can connect, then we'll do the peer-to-peer connection with that person.
Oh, okay, through the IP. Okay.
Yes, if it's not there, then we use NATs.
Got it.
And if you do establish a peer-to-peer connection, then, and only then, would you support the data file.
Oh, okay, like transferring files.
Yeah.
Okay.
So we wouldn't do it over. You lose the ability to have that over NATs. But if you choose to have a peer-to-peer, some people may still want to be anonymous and talk to you. They don't want to share where they are on the internet.
Yeah.
Right. But if somebody's willing to give you the peer-to-peer and we establish that, then you could do a data file transfer over that. See what I'm saying?
Yeah. Okay.
And so we leave the two sort of options open for this, right?
Yeah. Interesting.
And then we could still do group chats over NATs. What's the big deal, right? We'll figure that out
Yeah.
too.
And
I don't want to create another stream. Like I don't want to add any more of that complexity. We just figure it out. But we could do group chats where we do have, if everybody's in a cap, maybe cap to cap, maybe. I mean, we can get there.
Yeah.
But bare minimally, I'd love to try to do that. Right?
And separate it based on if they want to transfer a file or not.
If this person if we have an IP address,
Yep.
then we can do that. Now, here's the next question. It might be good to add a connect button. So you're not necessarily connecting by default.
Like as in connecting with your IP or in general?
The peer-to-peer connection.
The peer-to-peer. Okay.
Because if I come up and I see you have it and your cap's not up, I'm going to spend all this time trying to connect, right?
Okay.
It might be better to, in the UI, if we click on the list or something, or double click or find some event, then, and we can change the color, then establish so we could start with NATs and say, hey, are you there? Yeah, all right, let's establish a peer-to-peer.
Got it. Okay,
right?
So check if they're active
we can
first.
talk and then make it on an on-demand thing, where then we sort of connect peer-to-peer on demand, and then we start using that sort of channel to talk to each other.
Got it. Okay.
Right?
Yeah.
Right, instead of an automatic thing. So we tie it to, let's run the system for a second. So if I come back here and do a make, what is it, run cap?
Yeah.
All right.
Boom, boom, boom.
And here we do a make run TUI. All right. Okay. So what I'm thinking is I can do this, right? But maybe if I double click this, we'll see if we can get that kind of event.
Yeah.
If I double click this, then if it establishes a peer-to-peer, we can maybe change the color or something to this.
Oh,
that would tell
okay.
us that we're in a peer-to-peer sort of connection as opposed to something else, right?
Yeah.
Or we add another button, which I don't think we need the button for that. I think we should be able to do it here.
Double clicking, yeah.
Now, I don't know if we can get that kind of event, but let's at least try to do that first, right? Is there a way to, we know the single click, that's fine. But if I do a double click, will I get that event sort of back? Right? That would be kind of cool. And then we can control it a little bit more. So let's first at least get that double clicking thing to work. And then we've got to figure out how do we put this in and bypass NATs because it's there and all that sort of stuff, right?
Like yeah, exactly. Like the logic behind that switching.
Okay. Notice that on my UI, remember on yours that
yeah, it was the screen size that was messing it up.
Oh yeah, we go bigger. Yeah.
It has to do with the height. Then.
But maybe that's just, what is the height that we did for this is the question. I mean, we shouldn't be spending time on this, but now I'm just...
I think it was like 85 and 15 or that we had set the proportions to.
Oh, here.
85, 15.
Right, and here I do a 90-10, right? But when I did 90-10, you didn't see it.
No,
What's your problem, right? Yeah. So it's interesting. Like there's I guess the way the margins or something work on that. And if I did 80-20, I mean, this is why I hate UI, right? But
yeah, like something small like that will
drive you crazy forever, right?
Yeah.
And I don't know if you put 0 here, what happens? Oh,
it just doesn't show up.
Like you would think there's a way to just tell it to, yeah, no, okay. I'm just gonna leave it. But oh, but what is this? 20. Just curious, man.
Yeah.
Oh, that was the width of that. Yeah, okay, that's fair. Okay, I'm gonna leave it. I was just curious. All right, let's see if we can get a. This was the list changed function, right? That's when it changes. But I guess we got the event for the click for free.
Look, it's. I think it was like currently selected or, was that it up there?
I don't know.
Event. Oh no. Control Q. Yeah.
Set input capture. That's for the. This gets called, I think, when we selected something. We may have gotten that for free because this is the list, right? And this is adding text view, app, query, scroll, list, set item text.
Main and secondary. Okay.
That's the text area. So this was the escape or the control. This is the button handler. What is AI toggle? Oh, that was the
That
AI.
was that.
Yeah. So I think we got this for free.
It just knows with a list that you can.
So
click
my
certain
question then
items.
is list dot, come on. Is there a input capture?
Set mouse capture.
Maybe. Okay. So there would be two things, right? Set mouse capture sets a function which captures mouse events containing the original T-cell mouse event. They're forwarded to the primitive's default. This function can then choose to forward the event. So, oops. Yeah. I hate doing things like this. Just for the heck of it for a minute. So
there's an N at the end.
Oops. So the question is action, a T-view action. It would have been nice to have a mouse. Here we go.
Mouse. Okay. Left double click.
Yeah. Left double click. So if action equals this, you would think the action would be enough, right?
Yeah.
What if I have the text view already here, right?
Yep.
How do we write to the text view? I just wanted to hack something here.
Yeah, just to make sure it recognizes.
Yeah, like that. But it needs it in a slice, right? just to see if it recognizes it. And then return action and event. Because I think it said return that back to the.
Want to know about?
I still want the other thing to get called. So the reason we did this here and not in a separate function is because we needed to leverage closures for some reason. Everything else, well, I guess we did it all here. Oh, we put it in a function and then wrapped it that way, didn't we?
Yep.
But there was something about this that we couldn't put in a separate function because we needed to access some state, and passing it in was a nightmare. And yeah. Anyway, let's just say we did that. Let's just see if this works. I don't know.
Yep.
Double click. Okay.
Beautiful.
Okay. Cool. So that solves that particular problem, right? And that would mean too that we could write a function to sort of handle this as well. Okay. So something like user
or like direct connect.
Oh, but we would need to know some information here. Like,
well, what user it is.
I know. All we know is that we did a double click, but it would be the selected user at least.
Yeah.
Yeah. So that's fair, right? Plus, I don't think this needs to be. So let's just put this here for a minute. Where did we put the button handler? Down here.
Down there. Yep.
AI toggle. Okay, at the bottom, right?
And that's where we did the colors. Yeah. Okay.
So let's double check that this is still going to work. So, oh, but we have to be able to return. Oh, we do it here anyway, so it doesn't matter. Okay. So the only thing now is we need to remember, we need to know dot list dot selected. We must be using this somewhere, right? Get item. Where would we be getting the selected item in code already? Here, list
There.
get item, current ID. Oh, but that was, oh, here. Okay.
UI list get current item. Okay.
Okay, so I could try this again. So UI dot, what was that? The
Right.
text view, was it text view? Dot right?
I want to say yes.
Oh, man. Stop trying to help me. And then here I can do a funct dot sprintf. Double clicked. And let's just get the current ID.
Mm-hmm.
So we should see that now, right? Perfect.
Nice.
Okay. And then here we would be wanting to establish a connection, right? So like establishing peer connection, right? And now that's the current ID, but this would be the name, wouldn't it? Let's just see what that looks like.
some dots.
Oh, it's saying that already takes a right. Already takes a slice of bytes. So I don't understand why this is saying use from printf, and that's okay. It doesn't matter. I know what it's complaining about. So if I do this, I'll
Establishing.
probably put some dashes in there, but you see it tabbed it over though.
It did.
Instead of, oh yeah, I forgot about a pen. I guess this implements the IO writer. Okay. Oh, a space there. And those dashes become important, right?
That there. Yep.
Let's see what this looks like. Okay.
Nice.
Establishing peer connection with Kevin. Right. We can also check that we're already peering. Okay. So all of this is pretty cool, right? We now have a sorry, I'm taking a stretch here. We now have a place where we can double click and do whatever it is we have to do.
Yeah.
And then also lay out whether or not we've sort of connected or not. It's pretty good.
Yeah, that was pretty painless.
Yeah, I like this. I like this package we're using for all of that. Okay, so let's think about this now. We now need to add some infrastructure in place to, I'm going to save this work, but we've got to add some infrastructure in place now using our TCP package to be able to do all this and then maintain the server side. Maintaining the server side, that's fine. We have those events we have to implement. We have to manage our own client connections though.
Okay.
Right, because we've got code for both of that. So this handles the so we're handling the UI event that we needed. Okay. I feel like all this work in front of me right now, my brain is shutting down.
It's at that point where it's like, oh boy.
Yeah, there's a lot. Okay, there's two things now. We've got our TCP package, which helps to accept client connections and sort of manage the client connections, right?
Okay.
But we're missing the other side of this, which is we also need to make client connections. We're going to have more than one.
Yeah.
We're going to have to know who that's with. I wonder, remember, we're on the UI side, right?
Yeah.
So we're going to have to go and ask the server to establish a peer-to-peer connection, which could drop too. So if I come back here for a second, app,
Chat app.
that's the connect call that establishes the socket connection, right?
Yeah.
Okay. And this is the chat listening to messages coming back and forth. And where is chat located? Oh, we made it business. Okay. The chat bus handshake. Listen client. Listen client. Okay. This is interesting to me. Now, we created a command language, didn't we?
We did the share key, or yeah,
For the shared key, right?
yeah.
How does that work again? We need to see how that works again. Because we blindly, what do we do here? Signature, send message bus. Here. We sort of blindly, we blindly put everything on the bus.
I think that's how we did it.
But I thought if we knew that the person was connected to the same cap, send message client for a second. Send message client. That sends it back to, that's over the socket connection. Okay. Because that's listen bus. This is listen client. So an incoming message comes in from our client. We validate who it's from, validate the signature. We retrieve user information, right? We retrieving who it's supposed to go to. And then we send it over send message. Waits for messages from the user where we're reading a message. I'm assuming over a socket connection. Yes. Okay. So we read the message. It's incoming. This is coming from the client itself. And then we do send the client message. Now this client message, to con to, I find this one interesting because this is sending it to the socket connection. Okay. Or we have send message bus. Oh, the user might not be found. Okay.
User not found, sending over bus. Oh. So it is only sending it to the bus if we can't
Because
find
we
the
have a
user.
socket connection for everybody. That's what this storage is doing, right?
Yeah.
It's maintaining that. So if we find it, that means that they're connected to the same cap. I don't know if we've ever tested that. If not, and it's that the user doesn't exist, then we send it over the bus.
Got it.
Okay. Send message bus. In which case, we publish it. So, right. So anytime a socket connection is established to our cap, we are adding it to the store. And that has to be happening somewhere too. That's on the handshake. Let's see. Yes, somebody's come in. We go back to the handshake. We go upgrade it to a WebSocket.
Yeah.
We go back through. We add that user now to this, so we will know. So when it comes in, we look, do we have a socket connection? Yes. This error got me sort of confused because um, this logic might be, see how there's little here and a lot here?
Yeah.
I'm wondering, normally I don't like to do this, but this sort of is the small case. I'm just wondering.
Oh, okay. So like this is less, so put it above it,
Maybe.
basically.
It might help with readability here.
Yeah.
So retrieve, right? We found the user. So we'll just send it to them directly.
Yep.
If the error is not exists, then we'll send it over the bus. So we just spent a bunch of time here, right?
Mm-hmm.
Is what I'm saying. So
This would be a case to put a comment to kind of speed up the understanding.
right. Yeah. I think so. I might even just keep the comments like this. Normally, you wouldn't want this if off this error variable.
Okay.
Normally, you wouldn't want, like, that's harder to read from a Go perspective. But the thing is that we're using this to help with that, right?
Mm-hmm.
And so I could put all the comments above also. I use that 80 gutter for messages. I can keep that. But I have a feeling because it's not equals nil, your eyes are assuming this. Like I get in trouble like this. This is always,
yes.
your brain isn't going to see it.
Because you see the not equals nil so much.
Yes, that's where your brain is, right? And so this is just a really weird situation for me. I got confused because I looked at it as an error case where we weren't sending messages because we failed. But in reality, right, I think for readability, we have to come in and do this. Right, and now we can say we don't have a WebSocket connection for the users, so send a message over the bus. But it's only if the error, like if the user is not exists. Now, we could do the following. I think to even clean this up a little bit. I love switch statements.
Mm-hmm.
I really do. But this might be a case also where now I broke something here. I broke some here. I don't know where that information, like where that went. So let's just take a look at this for a second. This is the original code. So either way on the error, we went to a continue. And this message was bad because we didn't really send it over the WebSocket here if we were sort of here, but we never got to this line. So this was really for this because that was a continue, right? So this was about this.
Yeah.
And then I did this after. This one is before. So I think for consistency,
Just do it before also.
yeah. So I don't know if this reads better, right? It's like retrieve. Maybe I can put this here.
Yeah, that's where I was going with it.
If the user is found, send the message directly to the user.
Mm-hmm.
We do this, and then we continue back to the top of the loop. Okay, fine. Then here I got to kind of says if we don't have a WebSocket connection for the user,
We send it over the bus.
send the message over the bus. And here we're just checking that it was user not exists. And then if not, error. A little bit more code. And it's a little bit more code, but I think this is clear.
I think breaking it up like that helps you understand it, and the order of it too.
Yeah, because we're about to have a third case now, which is the peer-to-peer,
Yeah.
which is sort of going to come in here, right? I don't know what that looks like yet, but it's going to be sort of a third step where we do this first, then it's peer-to-peer, and then we have it there. So that would be on the listen where a message came in from our client, right?
Yep.
And the problem now is baggage. Because when we have a peer-to-peer, we're going to say the cap becomes both a client and a server.
Yes, that
and
was
so
okay.
So you see what's happening now? And so in our brain, this is what we've been doing.
Listen,
We've
UI.
been thinking about it as from a UI perspective, right?
Mm-hmm.
And so this is really like we want to listen to the UI, whatever the sort of UI is, right?
Yeah.
And I could even argue right now that we call this the UI handshake. Okay? So we're going to perform a UI handshake. Now, I don't like this where we used UI in the beginning here and we put it at the end. So we should be consistent here, right? Should be consistent.
I like UI at the end.
You see, I was going to say the beginning because then we have a prefix for everything that's UI related.
Okay,
instead
of a suffix. Okay.
Yeah, it also helps at some level with tooling later on, right? So, in other words, if I do this, right? If I do this, right? What also gets interesting for me, just for now, and this is where you're trying to establish better mental models around the code, okay? I know this is specific to UI. I know this is specific to UI related stuff, right?
Yep.
All right. So
same package, just different.
Same package, and I normally don't like to break up a method set, but no.
It didn't bring it over.
No, I know. I just have to look at what it was. Weird. Took out HTTP here. No, it's there.
It was a WebSocket, the Gorilla.
Oh, the Gorilla. I know, but when I just looked at this, this is telling me that it's. Oh, this is in the original.
Yeah, different.
Sorry, bro. And this was new. So, all right, good. We're missing that. Okay. So I know that these are UI related for just a minute. Normally I wouldn't want to do this, but I'm trying to get a better understanding of. Okay, listen bus is when we're listening for data off the bus. Is critical error. Read a message. Now, this is reading a message off of the WebSocket. So I could call this UI read message, couldn't I?
Yeah.
Because anything's off of a WebSocket is UI related.
And so that would move.
So you put that there. And I like to just know I'm dealing with unexported sometimes. So just do that. Okay. This is sending the message over the bus. This is the ping-ponging thing. I forgot where that's used. That's it.
Wasn't that with the handshake?
Yeah, I just don't remember where that function is. There's the ping.
Oh, okay.
I don't know where. Like if I do this, I'll know right away. There's the ping. Pong's being used on the UI side, right?
Yep.
Okay. So again, what I would do
UI.
So everything related to UI communication, right? From the handshake to listening for messages to reading a message, and the Pong is there. Then everything here right now, send message client, that's over the WebSocket, right? UI read. UI send
message.
Yeah, I want consistency. So that's read message. It should just be UI send message, right?
Yeah.
Yeah.
Take out the client.
All right. This is the refactoring people don't do. Right? We've been developing this over a couple months.
Yeah.
We're now at a point where we're going back and reading the code again and realizing that we had to spend all this time trying to remember things. Comments aren't necessarily always the answer. Sometimes they are, right? The comments I think we put into this other code here became super important, right? In fact, I would almost argue sometimes I like to just do this to get it off, just to say, hey, read this.
Yeah, make sure.
Right?
Make sure
Instead of it's attached when it's something like this. But what we're doing now, I think, is we're refactoring again to keep our brain, because we're going to have three things going on. We're going to have UI, we're going to have the bus, and then we're going to have our peer-to-peer stuff.
Exactly. So
right?
Separating that kind of helps you just find things, and two, just understand when you come back later.
Yeah.
That everything is okay. We know there's three things going on.
So
here.
we have a UI listen, which had to be exported, right?
Yeah.
So, and I might not keep this. I'm just right now letting my brain sort of play this out. So here's listen bus. Maybe what we want to do, let me take this out here for a second. Okay. Jetstream. Here we go again.
Yep. These are also big functions too.
Yeah, and I really can't, maybe can make them smaller, but now what if I rename this to bus listen? Again, bus sort of centric here, right? So we've got the new, I've got this critical, I've got send message bus, unexported. All of this will be unexported. Maybe this becomes bus send message, right? Just like we did here.
I didn't rename it.
I didn't rename it. All right. So we had UI send message read. Okay, we'll just do it ourselves. UI. Oh, not UI, bus. Let's see what goes red. So if I do that, this went red here. So this is bus send message. Okay. Now what bothers me is this was a listen call, wasn't it? Which is a function. Let's see where this is used. It's used here. So this is a function that is a read function, honestly, right? So since we have a UI read message, where is it?
UI read message. Yep.
Maybe we call this bus read message. Okay. And because that's what it's doing. When this gets called, a message came in. We're reading it, right? We do all this sort of work. And then that's the sending on the bus. And this was the reading of the message off the UI and the sending, right? Which we know is a WebSocket at the end of the day. And this is the big listen that the app layer has to call to sort of get everything going. Yeah, which blocks on that read. Now, what is left here is the new
The is critical.
is critical and the ping. But my guess is the ping. Where is the ping used again?
I think
I think
in
it's
the
used
new.
at the top. Yeah. So we put the ping in here.
Mm-hmm.
And this is at a ping must walk through a list or something. Yeah.
Yep. Walking
Goes
through
through a
the
list.
connections.
Which has to be already, yeah, gets coffee. So here's the ping. That's fine. Now this is, I would say, UI related. That's who we're pinging. Anything connected. So what I would do is put this back here. Call it that. You get the UI pong.
UI ping, UI pong.
And technically kind of ping pong. So let's do that. So now what we've done, assuming we didn't break anything, right?
Mm-hmm.
Is separated the functions that work with the UI connectivity, which right now is WebSocket based.
Yeah.
There's read UI, with the bus, which is NATS based, which is basically reading and publishing. Which calls UI send message, right? When something comes in off the bus. Now that's assuming that we have it. So I find that super interesting. Did we, oh, because we did the store. Oh, so we have the same situation here, right? So we have the same sort of situation here.
Mm-hmm.
So the work we did here was this, right?
Yeah.
So let's see if we can sort of marry this here. I didn't get rid of some here. No, okay. Let's go back. Right, if error equals nil, right? So if error equals nil, then what we did here was the log and the UI send.
Yep.
Which is these two things. And in our case, we need to continue, but we're not in a loop here. So I would say we need a return. Okay. And I need a from. So if the user is found, send the message directly to the user, right?
Mm-hmm.
Then we wrote to do, but and then if we don't have, which was this if here, right?
Yep, it was that. Okay.
Then we do this.
Yep.
And we can do a return here just to keep it clean. Then the default would have been this. And I don't need a return because we're at the end of that function. Right?
We're returning F.
Yeah. But in this case, if we don't have a WebSocket for the user, ignore the message.
Got it.
That's what we're going to do here.
Now bus and UI are matching.
I think so, because,
flow.
right, it's matching flow. And I kind of like this order because this is really the order of precedent.
Yeah.
Send it over the socket first, then the peer, then the bus.
Yeah.
So we put the logic back so that could be, if not, like, it's not the order that we are thinking about these things in. So here's a case where maybe we are not being completely idiomatic.
Okay.
Isn't helping our mental model, because putting this in the right order of precedent is going to help our brain understand that, yes, we want to do WebSocket first, then peer-to-peer.
And then catch-all is the bus.
Yeah. You see?
And it makes more sense.
And now we know where to put the peer-to-peer stuff.
Yeah.
Like, we have it. You see what I'm saying?
Because of that refactoring and reading through that.
Yes, because my brain was looking for this sort of order, and it wasn't there.
Mm-hmm.
And so somebody first reading this might go, this is an idiomatic, move the error up.
Yeah.
And then my brain's going to come back and say, you can say something. This is what I would sort of do in a production code. We want the logic to sort of match the order of press. I don't know.
I think it's a C.
I'm going to precedence. That's right.
I think, okay, yeah.
Well, this is what I do all the time, bro, because I'm a horrible speller, man. Just do this.
Okay,
and
yeah.
I was right. This is it, right? Do it all the time. The sort of order we think about sending a message, right? So we've got WebSocket, peer-to-peer bus, right? And normally when I do that and somebody sees my name, it's like this wasn't done randomly, or
yeah, it's
like,
not something that's missed.
Yeah, it wasn't something that we were missing. We just wanted to do things in this order, right? And we just, instead of calling this WebSocket, we always think about it as the UI. But I want to use the word WebSocket here because that's more tied to the connection. All right. Let's make sure we didn't break anything. Let's start there. So I won't be able to test this until I push it and you can run it. So let's add all git commit just a. So I would call this a mental model refactoring. So pull that down. run your cap, then run your TUI.
All right.
I'm going to send you a message. Hi,
Got it.
Kevin. All right, send it back. Okay, so we all know that's working. Good. So I think what's nice now is when we come back, when are we coming back? On Thursday.
Yeah, Thursday.
When we come back on Thursday now, when we come back on Thursday, we're going to have to do something. We need to be able to manage client connections, just like technically this manages incoming connections. We've got to manage outgoing connections.
Okay.
All right. So the code that we've got to kind of hear on the dial in this code here. So we have two choices. We can build that into the TCP package. I don't think that's
It seems
good to do.
specific.
I mean, it could belong there, but this is already a big package. I wouldn't know how to begin organizing it. So we can make a new foundation package, or we add a new business SDK package, which we don't really have any. Oh, that's app level. We don't really have any support packages, but I think this is something that's reusable. So I think what we do is we need basically a TCP server implementation, which is what this is. Okay, this is our TCP server implementation. We need a TCP client implementation that will let us make connections, manage those connections, and deal with drops, and then change our hack program to use sort of that package. Calling this TCP now feels too generic unless we add another. Problem is I have this client already. Now that might be good, right? Like we have this support already. It already knows how to read. So maybe we can put it in here where we change this to be server.
Okay.
Right? And then we have a clients manager already too. We have a clients manager already. So what might be interesting is we have the concept of a client. This might have to become exported. We've got the idea of client management already. This really is much more of a implementing a TCP server, isn't it?
Yeah. New server. For the comments, Copilot is awesome.
Yeah, it does.
I love using it for that.
You see, this is much more of the server side of things, right?
Mm-hmm.
And then if you come back here and we look at main, right, it's going to be a new server. And yeah, but this is interesting because the config, this is probably more for server config, right? I don't know if we'll have a client config, but let's just do this for now. So this is more of a server config. When I look at this, right, the server config, it takes a server config. That was our little thing here. But I don't have a TCP go anymore, which is a bummer. So maybe config now is what we would call TCP.go, but we'll deal with that one later.
Got it. Okay.
But this is more server stuff, right? Yeah. So what we need now is this represents a client in the system. It has everything that we need in it,
Yep.
right? With the interface that would be involved. This is a collection of clients.
Yeah, that's the map.
What we don't have is the ability to sort of abstract the dial so then when it connects, it sort of comes into this list, right? We got to think about what the API looks like for this situation. Because we've got the dial and we have the close, and we have to do all this. All right. And then we end up with a connection. But this manages a client. And a client, in our case, takes the TPC. So here's a problem already. This client takes a TCP server and a NET connection. Oh. So this is easy because it just wants a logger.
Yeah.
And this can be easy because we already have an interface for it. So we need to get rid of TCP server, and we need the interfaces for these two.
For process and the other
For
one
these
was
two things, right? Like we have it's bad because I don't know where the interfaces are here. It's this interface, right? So ideally, what this really should be saying, and we'll do this next week, or we'll do it on Thursday, is this should be taking the interface here and a logger. Now we can use it for both sides of the equation.
Got it.
So we got to clean that up. And then if we're going to call this server, which it is, we got to have something called a client manager that lets us do the dial and get back this client. And we might have to integrate some of that back into our server. So unfortunately, we got a little bit more work to do here because we're not just a server. We're also, and it's almost here, right? We just got to sort of clean this up and build that part of the API, because then once we do that, I got to push this. Once we do that, then this other work we did here, all this gets easier.
Got it. Okay.
Before I do anything else, then let me push this. So
Git add.
So when we're here on Thursday,
so we still have some setup work basically.
We have to add support, so we also can handle us being a
both client and a server.
Yeah, but a multi-client, so we can have multiple client connections. You know what I'm saying, and manage that. Like 80% of the code is there. We just don't have a small part of the API. But since the server also has to manage client connections, if we build that API right, not only does the server use it,
but the client.
So we've made it all internal to the server. What we have to do is write that in a way where the server can use it, but it's also exported so we can use it. So we're going to have two things. We're going to establish a TCP new server and a TCP new client manager.
Got it. Okay.
We need both.
Yeah.
Yeah, and we already have the to-do where we're going to sort of leverage these things.
Yeah, where that's going to go.
Yeah.
Cool.
All right, so I just pushed all that code here. So where are we? I remember where we're going. Here. Okay, so at the top of the hour, we got other work to do.
Yeah.
But this wasn't bad. This was a good sort of refactoring. We'll finish this refactoring again on Thursday. And then I think it's going to be a really clean plug and play to get it now in the business layer, sort of where that needs to be.
Yeah.
Yeah.
And that refactoring of renaming things and separating them, I like watching that because that itself clears up a lot and speeds you up later.
And that's what people don't do.
Mm-hmm.
And so if you're lost, forget about the guy that you don't even know yet.
Yeah, that hasn't seen
That
the
person
project.
has no idea what's going on, right?
Exactly.
It's just not fair to them.
Mm-hmm.
So you got to do these refactorings in those moments. And I know it feels like we just spent 2 hours and we didn't really accomplish anything, but you're going to see how quick
The next
Friday is going to be, and
Yeah.
there won't be any bugs because we found a way of puzzle piecing that in. Remember, if you're not changing logic and you're adding, that's always going to be the home run. The moment you have to change something, you potentially broke something. But if you add code, then technically, ideally, you didn't break anything that it's existing.
Yeah, it should.
If
Whatever
something
you added.
broke, it's around what you added, not what you changed.
Exactly.
And then over time, you can come in and maybe be a little bit more efficient in that area.
Mm-hmm.
But you got to get it to work first, because how many times
Yeah.
did we make a change and then it broke? Not a lot, because I do it constantly.
Mm-hmm.
When I was your age, I would make these changes for 2 hours and the thing would be broken. I'd be like, I don't even know where to begin.
Yeah, where do you start? Now it's like overwhelming.
Right? I didn't expect any of that to break. So
I've already experienced some of that.
bad. All right, I appreciate everybody hanging out, and we'll see everybody again on Thursday.